All right, so let's move on to section 2.5. We're going to transform quadratic functions. All the rules that I gave you guys earlier in chapter 2 apply here, okay? So the only difference is we're applying it to quadratic functions. So all the rules were transformations. So over here I have a quadratic function, and it's going to be centered at the origin. And so let me use a white marker here. So a quadratic function, f of x is equal to x squared, right? The vertex is at 0, 0. All right, so now if I ask you, what does this blue function right here do, right? Is this x minus h? Again, it's counterintuitive, right? You would think it's, shift it h units to the left. It's actually h units to the right. And if I ask you, what does this red function do here, right? X plus h means you shift it h units to the left, okay? Very, very counterintuitive. And, if we were to actually plot this, right, h units to the right will look something like this. Here's h. And your parabola does not change size, okay? And if I say shift it h units to the left, the red function would look something like this. All right, so those are called horizontal translations. It does not change the size of the graph, it just shifts the position. All right, moving on to number 2. Again, we have our parent function, f of x is equal to x squared. So let's graph that. And this time we have a vertical translation, right? If I ask you, what does this blue function, this plus k do? You say, well, basically the k shifts the graph up k units, right? And if it's minus k, it shifts your parabola down k units. Okay, so that should be fairly easy to sketch. Let's do the blue one here. So if it was at 0, 0, it gets shifted k units up. It will look something like that, right? And then for the green function, this time I'm using green, if I shift it k units down, right, it will look something like that, right? You could write minus k if you want. So you could write minus k over here. Let's just do that here, minus k. And then over back here, right, you could write minus h if you want, okay? All right, so vertical translation does not change the size of the graph. It just shifts it up and down. These should be the same size. Again, I'm sketching it to the best of my ability without any, computer graphic tool, if whatnot. All right, so let's take a look at number 3. If you have a negative in front of the x, right, this means it's a reflection over the x. And if you have a negative inside the x, right, parentheses squared, this means it's a reflection over the y. All right. Let's see what that looks like. Okay, so f of x equals x squared. There's my parabola at the vertex of 0, 0. Now, reflection over the x, right, that is fairly straightforward. It just looks something like this. Right, the parabola basically goes down. Now, what about reflection over the y? Well, here is my x-axis, here's my y-axis, right? If I reflect every point across the y, right, here's x, comma y, right? Well, this point would just be right here, right? Negative x, comma y. And so if I reflect my original parent function over the y, it just ends up being the same graph, right? And you can see that from just the algebra right here. If I show you real quick, right? Negative x quantity squared, well, that's just x squared, right? It's just the same exact graph. And so a reflection over the y-axis just ends up being the original graph itself. And you could see this algebraically why it's true. Okay, reflection over the x, it means it goes down. Reflection over the y, you end up with the exact same graph. Okay, so it's one of those tricky things where it's like, if you draw it out, you could hopefully see that. All right, now, examples 1 through 3 does not change the size of the graph, right? And those are translations and reflections. 4 and 5 are stretches and shrinks or compressions. Okay, so let's take a look at 4 and 5. Over here, if I ask you, you know, if I ask you, what is this, right? If the absolute value of A is greater than 1, you would say it's a vertical stretch, right, by a factor of 1 over A. And over here, for the green function, right, if A is between 0 and 1, you would say vertical. You could say shrink or compression, okay? Either word is fine. I'm going to abbreviate by factor of 1 over A. Okay, absolute value of A. All right, now you may be wondering, it's like, okay, I can memorize these words, but what does it actually mean? So I will show you this on the graph right here. Here's f of x is equal to x squared. Okay, so there's my parent function, right? And now I'm going to draw the blue function. A vertical stretch, what is that? A vertical stretch just means you pull away from the x-axis, okay? So if I pull my graph away from the x-axis, it's going to look something like this. In other words, the new graph becomes narrower, okay? So vertical stretch pulling away from the x-axis, away from the x-axis. It takes my original graph and pulls it away from the x-axis. That's what a vertical stretch means. And so in comparison to the parent function, it looks narrower, right? All right, so the opposite of that is true if you have a vertical shrink or compression. If you have a vertical shrink or compression, your new parabola is going to look something like this. And you might have guessed, right? A vertical shrink means I pull towards the x-axis, right? The graph basically gets crushed, and therefore the green graph, right, if the absolute value of A is between 0 and 1, is wider than the parent function, okay? So one graph becomes wider, the other one becomes narrower. That's what it means to vertically stretch. Pull away from the x-axis. Vertically shrink or compress means to pull towards the x-axis, okay? And hopefully that makes more sense visually now. All right, so what about part number 5 right here? So on number 5, you know, if the absolute value of B is greater than 1, it changes the size of the graph horizontally, right? It's a horizontal, not stretch, but a horizontal shrink or compression, either word's fine, by a factor, okay, this is where the wording is a little bit tricky, by a factor of 1 over B, okay, 1 over B. And actually, I saw my mistake. Some of you might have seen this. On the previous one, I was thinking horizontal. Okay, so we're going to make some corrections over here. This should just be a vertical shrink by a factor of A. Okay, and this should just be a vertical stretch by a factor of A. So I apologize if I caused some confusion. Okay, so the vertical one is just the factor of A itself. The horizontal one is 1 over whatever that factor is. Okay, so please make note in your notes. Oops. So if the absolute value of B is between 0 and 1, we call it a horizontal stretch by a factor of 1 over B. Okay, so these guys are 1 over something. The A is just, the vertical stretch or shrink factor is just by A. All right, so please make that correction in your notes. All right, so again, right, you can memorize the wording, but you have to see what does it look like graphically when you say horizontal stretch or shrink. What do you mean by that? So hopefully you can understand after I explain this to you. So here's my parent function. And let's start with the blue function, right? The blue function says it's a horizontal shrink or compression by a factor of 1 over B, all right? Horizontally shrink. Horizontal just means, you know, think of a horizontal line, right? The horizon. And so if I horizontally shrink or compress a graph, I'm going to pull it towards the y-axis, okay? So pull it towards the y-axis. In other words, I'm going to take this graph right here and I'm going to push it towards the y-axis. Okay, take my original parent function, I'm going to push it towards the y-axis. Okay, so that's what a horizontal shrink does to the graph. It pulls towards the y-axis. Now, what about a horizontal stretch by a factor of 1 over b? And you might have guessed, right? It's going to pull away from the y-axis. Okay, so it's going to take my parent function and pull it away from the y-axis. Pulls away from the y-axis. All right, so hopefully that makes sense visually. And now you can think, right? Pulling towards the y-axis, which is a horizontal shrink, right, is the exact same thing as a vertical stretch by a factor of a, which is pulling away from the x-axis, right? And likewise, a horizontal stretch by a factor of 1 over b, if it pulls away from the y-axis, right, takes my parent function, pulls it away, it's the same thing as a vertical shrink or compression by a factor of a, which is a pulling towards the x-axis, right? This looks just like this, right? Except you're stretching horizontally or shrinking horizontally as opposed to stretching vertically and stretching horizontally. Okay, so again, vertical stretch is the same thing as a horizontal shrink. Vertical shrink is the same thing as a horizontal stretch. So if you're like, hey, these two graphs look exactly the same, you're correct. They both do the same exact things, except it's just stated in a different way. All right, so the very last thing that combines all the transformations is it's very helpful to know the vertex form of a parabola. And the vertex form you may have studied before is quite simply a x minus h squared plus k. All right, so h comma k is your vertex, right? A changes the size of the graph, right, vertically, and if a is less than 0, of course, the parabola goes down, and if a is positive, right, the parabola goes up. Okay, so you may have studied that in Math 2. So here's some kind of parabola, vertex, h, comma, k. All right, and this is for a is positive. So it's very, very helpful to know the vertex form because you can describe the transformation, right? H tells you the shift in left and right. K tells you the shift up and down. A changes the size of the graph vertically. And it also tells you if there's a reflection across the x.